Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. So inshallah today Madam going to continue our lesson on chapter 7, topic of magnetism, final part, which is part 3. So let's begin with magnetic field of a current loops and solenoid. Previously we've learned about what is magnetic field, the effect of the magnetic field on a moving charge. Okay, secondly, if you have a bundle of moving charge within a long straight conductor, what will effect of the magnetic field on the conductor itself. Then after that we move to another level where we're going to take a look on the B produced by the long straight conductor having current I flow within it. Then it brings us now to another level where we're going to see if the conductor now is not straight, it's a loop. Okay, it's in term of loop. Okay, and then after that further on solenoid. Okay, if let's say you have a conductor being bent into a loop, okay, there is a current flow within the conductor in this direction. From top view of this, like this one, right, we're going to see that, okay, the pattern of the direction of the current flow within this loop conductor will be counterclockwise direction. Okay. So by using Grab's rule or right hand rule number 2, we are going to determine the direction at the center of the loop, the direction of the B at the center of the loop. Is there any B, okay, out part of the loop, okay, at the outer part of the loop? Yes, there is B, this one and this one, but then it's not that strong, it's weak, okay, so it's not effective. The one that we're going to focus on is at the center of the loop, because this one concentrated, very strong and effective to us. Okay, so by using Grab's rule, place your thumb along the direction of the I, grab the conductor. You will see that at the center of the loop, okay, from this point of view, the direction of the B is out of the center of the loop. Alright, so this is in real life. Okay, let's say you have a loop like this, a conductor in term of loop, there is current flow within it, placed within a plane of pepper blue color here, and distribute iron filling surrounding or on the top of the pepper. You will see some pattern produced. Okay, this pattern is actually pattern of your B, magnetic field line, represented by the pattern of the iron filling here. Right, so magnetic field of a current loop equation is actually for a single loop, okay, it is considered as combination of, okay, 4 long straight conductor that's going to be combined become one single loop. Therefore, the formula of it, okay, B at the center of the loop is equivalent to mu naught 4 times of mu naught I over 2 pi r for one single conductor, right, where, okay, it's equivalent to 4 over pi, right, mu naught I over 2r, which is equivalent to, okay, 1.27, right, mu naught I over 2r. Okay, 1.27 here normally considered as 1 only, because 0.27 does not really give any big effect. So finally, the formula going to be for a circular loop. Okay, for a circular loop, B is equivalent to mu naught I over 2r. This is for a circular loop, one single loop. If you have more than one single loop, you're going to have redefine the formula by multiplying by the number of the loop. Mu naught I over 2R. Okay, this is with n loops of coil. Right. Magnetic field of a solenoid. So if you have more than one loop, alright, so you're going to have like this, okay, initially. If it is far away from each other, then the pattern of the B will be in this direction, okay. How to get this direction? Grabs the side that, okay, having the one that nearest to you, that obviously physically can be seen by you, okay. You will grab, this is the direction of the current, this is what? Into the page, this is out of the page. Alright, so you will get the direction of this by using right hand rule number 2 or grabs rule. If the wire being bent very near to each other tightly, so it becomes this figure. For this figure, we call it as solenoid or electromagnet. Why is it the name of it electromagnet? Because it's only produce magnetic behavior whenever there is electric or current flow within it. So the pattern of the B produced within the center of the solenoid in these directions. Alright, so this one, the pattern of the B produced here is similar to permanent bar magnet. So in industry, it's always practical to have solenoid or electromagnet instead of permanent bar magnet. Right? Next one, magnetic field in a solenoid, the magnitude of it. So the B is equivalent to mu naught n I. Small n here is actually the number of the turn per unit length, or this one. Okay. Right. So if let's say you want to rearrange it, B equivalent to mu naught n I, or mu naught n over L I. Okay. So you may do example 19.9 with its exercise. Take it as your task or homework. Now 19.10 domains. Magnetic effect of electrons. Talking about the orbits. Alright. So an individual atom should act like a magnet because of the motion of the electron about the nucleus. So every single thing in this world consists of very basic unit, which is an atom. Within an atom, we have a nucleus and electron orbiting the nucleus. The cos by of the electron orbiting the nucleus going to give a magnet effect or become magnet. The material become magnet behavior. But then, okay, however, okay, why is it so, by the way? Why is it so? Still remember, surrounding a moving charge, there will be magnetic field. Okay, surrounding a moving charge, there will be a magnetic field. So this is the one that we're talking about in this point. However, the magnetic field produced by one electron in an atom is often cancelled by an oppositely revolving electron in the same atom. Why? Because normally we have a pair of at least, a pair of electron at least. So if the first one is revolving or orbiting the nucleus in clockwise direction, the other one going to be counterclockwise direction in simple. The net result is that the magnetic effect produced by electron orbiting the nucleus either zero or very small. So it's not really does give effect, okay, on most material. Alright, that is why most of the material does not showing their magnetic behavior. Right? Then now we're going to talk about electrons still, but about the spin itself. Okay, instead of revolving or orbiting, instead of electron is, this is a nucleus, let's say. Then we have an electron orbiting the nucleus. Okay, and then we have a second electron, okay, orbiting the nucleus. Instead of talking about how the electron orbiting the nucleus, the electron itself, while orbiting the nucleus, is also spinning. Okay, so it has spin. Classical model is to consider the electron to spin like tops. Okay, it is actually quantum effect. What is quantum effect? We're going to discuss it in detail in last topic. The field due to the spinning is generally stronger than the field due to the orbital motion. Actually, the spinning effect is bigger. Okay, it's bigger. Then electrons usually pair up with their spins opposite each other, so their field cancel each other. This is by Sunnatullah, the way Allah arranged the position of the electron within a level of energy. Okay, normally in opposite spin, to make sure that they are going to cancel out their spin in simple. Alright, that is why most material are not naturally magnetic. Okay, how good, how brilliant Allah is. Alright, can you imagine if everything in this world has magnetic behavior, then we're going to stick to one another. We cannot move simply, isn't it? That is subhanallah. Okay, mashallah, very good. Right, magnetic effect of electron, the domain now. In some materials, the spin do not naturally cancel. We do have, but not most of the material. Some material. Such material are called ferromagnetic. Okay, large group of atoms in which the spin are aligned called domain. So what is domain? Domains is actually a large group of atoms where the spin are aligned in the same direction. When an external field is applied, the domain that are aligned with the field tend to grow at the expense of the others. Okay, this causes the material become magnetized, and it's going to show the characteristic of magnetic material. Domain continue. This is in terms of how to visualize what is domain and how the domain going to be realigned when we have external B applied to the material. Initially, let's say we don't have any external B applied to the material. Randomly, the orientation will be like this. The orientation of the domain. What does that mean by domain? Domain is actually a bundle of atoms that having same alignment of spin. Okay, so this is one domain, this is another one, this is another one, and this is another one, and so on. Right. When an external magnetic field B is applied, the domain tend to align with the magnetic field. So now they are going to combine. For example, this one. Okay, this is actually combination of few domains here. Become bigger. Okay, and they tend to follow the direction of the B. If the B even stronger, okay, if the external field applied is even become stronger, okay, more domains going to combine and going to follow the direction of the B. Okay, whenever they follow the direction of the B, in simple, they are going to have a bigger or a more effective magnetic behavior. Okay, types of magnetic material. The way they respond to the P that we applied just now, the way the domain realign and recombine. Okay, we can classify types of the magnetic material based on that, based on the behavior of the domain. We have three types of the magnetic material: ferromagnetic, paramagnetic, and diamagnetic. So what's the difference? Ferromagnetic material have permanent magnetic moments, okay, that are aligned readily readily with an external applied magnetic field. Paramagnetic have magnetic moments. What does that mean by magnetic moments? The effect of the spin just now. Okay, that tends to align with an external applied magnetic field, but the response is weak compared to a ferromagnetic material. That is why the name of it para. It means that weak, half. And diamagnetic, an external applied field is induced a very weak. Okay, it's not only weak, it's very weak magnetization that is opposite to direction of the applied field. Is very weak and is opposite to the direction of the applied field. That is diamagnetic, means that it has a behavior that opposite of the magnetic field that we want. Right, Islamic perspective view, point upon even the spin of the electron, right? A very small thing. The electron itself is a very small thing. It has mass of, it has mass of electron is 9.31 times 10 to the power of negative 31 kilogram. Okay, very small. The amount of the charge, okay, the E has negative 1.9 times 10 to the power of negative 19 coulomb of charge. These small things, okay, the spinning of it, the effect of it is very big in our life. So how brilliant Allah, mashallah, create things. As small as electron has a big effect in our life. Okay, the effect of the spinning of the electron going to cause whether the object going to be magnetic material or not. And we need or we use a lots of magnetic material in our daily life. For example, your ATM card, your hotel card key, you name of it, numbers of it, in loudspeaker, in electric guitar. So many things that we need to have magnetic material. All right. So and then how brilliant Allah Ta'ala is. Not most of the material or substance in this world going to show the magnetic behavior. For example, we do have electron in our body, but then we are not going to show the behavior of the magnetic behavior daily. Because of what? The arrangement of the spin of the electron already cancel out each other. Okay, so how brilliant Allah Ta'ala is. Then finally, of course, tutorial 7. Okay, page 649. Do not forget to complete everything. If you do have problem, please do not hesitate to contact me. Consult me, please. Okay, that's all for today. Thank you very much. And Assalamualaikum warahmatullahi.